Hello everyone, I'm Hojjat. Welcome to this talk. Today I will present our work Bullseye Polytope, which is a scalable clean label poisoning attack with improved transferability. Probably all of you have seen an image like this, where you have a picture of a dog. If you add some noise to that, then your smart neural network classifies the resulting image as a horse. This class of attacks, known as adversarial examples or evasion attacks, happen at test time. Today, I won't talk about this class of attacks. In particular, our attack is a dataset poisoning attack and happens at training time. In general, in dataset poisoning attacks, you put some poison data into the training set, so later on, when the victim trains the classifier on this poison dataset, you have your intended malicious code injected in the model. Our attack, though, is a continuation of a recent line of research where clean label and targeted poisoning attacks were proposed against transfer learning. Our attack is targeted. It means that it has no effect on the general performance of the model. The attack only happens for specific target samples. And it's clean label. It means that the poison data have correct labels. Now let me briefly explain to you what is transfer learning. In transfer learning, we have a large neural network which was trained on a large training set. We fine-tune that neural network on a small but similar training set. This fine-tuning process, named as transfer learning, is usually done in two ways: linear transfer learning and end-to-end transfer learning. In linear transfer learning, we only fine-tune the last layer of our network, our linear classifier. But in end-to-end transfer learning, we fine-tune all the layers of our neural network. And we call this second last layer, the blue neurons here, as our feature layer. And this layer and the layers before that are called the feature extractor network. And we denote this feature layer by F or phi during this talk. But how do we attack transfer learning? The goal is that the attacker wants sample T to be classified into class P after the fine-tuning phase by adding just some poison data to the fine-tuning set. Now let me give you an overview of the feature collision attack, the first proposed attack against transfer learning. In this attack, the feature extractor, which is used by the victim, is known to the attacker, so it's a white box attack. And the linear classifier is of course not known to the attacker because it's going to be built during the fine-tuning process by the victim. And the goal is that the attacker wants sample T to be classified into class P. So we as the attacker select X from class P. We add noise to that, it becomes X prime, such that features of X prime are close to features of T. So when the victim trains the linear classifier on this dataset, it learns to associate features of X prime with the class of P. So whenever it sees sample T, it will produce the output of P. Here you can see a simplification of the feature collision attack in a 2D feature space. The poison data from class P, class red here, are crafted in a way that they are pretty close to our target sample, the blue circle at the center. So when we have a linear classifier trained on this dataset, we hope that all this poison data and our target sample rely on the same side of the boundary. But what happens if the victim uses a different feature extractor network than the attacker? It means that the victim's feature space is different. Maybe in that feature space, the poison data and the target sample are not that much close to each other, so the boundary of our linear classifier happens actually between them. And in fact, this is the major limitation of the feature collision attack, that it fails in black box scenarios. To mitigate this limitation, the Convex Polytope attack was proposed. In this attack, poison samples create a convex shape around the target instead of all being close to the target. This is based on the mathematical guarantee that if you have a linear classifier that classifies a set of points X into class P, then every point inside the convex hull of X will be classified to P by our linear classifier. The authors of CP argued that compared to FC feature collision, CP creates a bigger shape in the feature space, so it increases the chance of transferability in black box settings. Although this is just an intuition, they have shown that CP outperforms FC by 20% on average. But how such a convex hull is created? The CP attack refines poison samples to optimize this loss value, which is computed over M surrogate networks at the same time. This loss becomes zero for each surrogate network when our target sample is written as a weighted positive average of our poison data. This is simply means that our target is inside the convex hull of our poison data by the definition. The authors of CP argue that by enforcing a convex hull around the target sample, CP creates a bigger attack zone, so the chance that this attack zone transfers to the victim's feature space is higher. But in fact, this is not necessarily the case. This is what happens in practice, that our target sample relies on the boundary of the convex polytope. Why? Because the moment that it gets into the convex hull, our loss value becomes 0, its minimum value. So, this bigger attack zone maybe is not big enough. With this intuition in mind, we propose Bullseye Polytope, where we fix the coefficients in the convex hull definition to 1 over k, where k is the number of poison samples. This simply means that we enforce our target sample to be at least very close to the center of the convex hull, which results into an arguably bigger attack zone. This also helps us to avoid optimizing the coefficients, which we found that pretty slow for the convex polytope attack. As you probably noticed, until now we only talked about linear transfer learning, where we optimize some heuristics defined over our feature layer. But what happens when we have end-to-end transfer learning, where our feature layer is constantly changing? In that case, similar to related work, we try to enforce the same heuristics computed over all of our hidden layers in the neural network, and in fact it's shown to be effective. We have done a wide range of experiments which you can find in the paper, and across all of them we were better than the previous works. But here I only report the numbers for the settings that were used by the state-of-the-art attack Convex Polytope. In linear transfer learning, BP achieves 10% higher attack success rate while being 7 times faster. In end-to-end transfer learning, Bullseye Polytope outperforms CP by 27% while being 12 times faster. But why is BP better? Is it the Bullseye idea contributing to its superior performance, or its faster algorithm allows for better optimization? To answer this question, we created 9 different variants of BP by setting the coefficient to other values. So we started from skewed distribution on top left with the lowest entropy, and we increased the entropy or shifted towards much more uniform distribution for the coefficients. On the bottom right, you can see the Bullseye Polytope. We observe the higher the entropy is, which means the coefficients are more uniform, the higher the attack success rate becomes. This simply means that the peak of the coefficient to be uniform actually matters. After we have submitted this work, we were notified of an independent benchmark. In this study, all poisoning attacks were benchmarked in a unified setting. In linear transfer learning, a setting that we have used also, the benchmark showed that our attack is better than others, sometimes with big margins. This benchmark studied a much more recent scenario, training from scratch, which means that you train your neural network from scratch on the poison dataset. This is a much more challenging setting, and it's specifically taken into consideration by another attack, which is Brew, which was published on arXiv parallel to this work. They have used 2 different datasets, CIFAR10 and TinyImageNet in the benchmark. In CIFAR10, we were worse than the Witch's Brew attack, but in TinyImageNet, we were actually better by 12% margin, which is very interesting because our attack was not designed for training from a scratch scenario. During this project, a concurrent study proposed some neighborhood conformity tests as a defense to sanitize the dataset against this family of attacks. We evaluated our attack against the only 2 effective defenses, L2 norm centroid and deep cannon defense, but here I only report the numbers for the deep cannon defense since it was the only effective defense against our attack. For each sample in the training set, this defense looks at its k nearest neighbors. If the sample's label is not the majority, it's removed from the dataset. In general, our attack was shown to be much more resilient against this defense in comparison to CP. For example, when K is set to 8 and we have 10 poisons, our attack success rate is 31%, while CP success rate is only 3%. But if you set K 2 times greater than the number of poisons, then both attacks are diminished completely. And it makes sense because in that case, the poison data will lose the majority voting game to the clean data. In summary, in our work, we propose a clean label data poisoning attack against transfer learning. It fixes an inherent flaw of Convex Polytope, which was the state of the art in this setting. It's an order of magnitude faster than that, it has a higher attack success rate, and it's also more resilient against defenses. Thank you for listening to this talk.